We're going to run through reading binary vapor-liquid equilibrium phase diagrams so that we could use them in binary flash and column-based distillation calculations, like those done using the McCabe-Thiele method. So the first place to start is either using a thermodynamic model to predict equilibrium behavior, such as the modified Raoult's law, or the Pang-Robinson equation state, or the unifact method, etc. Or you're going to look up experimental data collected and published in handbooks, such as Perry's Chemical Engineering Handbook or in scholarly articles. So we want to collect phase equilibrium data. Now we're going to use this data to generate our plots. I've collected phase equilibrium data for water and ethylene glycol at a pressure of 30.4 kilopascals. I got this from Perry's Chemical Engineering Handbook. And so this gives us the mole fraction of water in the liquid phase, and our Y is our mole fraction of our water in the vapor phase. So outside of these two temperatures, 69.5 and 160.7, we won't have vapor-liquid equilibrium. So now we have this data, we could create a TXY phase diagram. Basically what we do is we're going to plot our mole fractions on the x-axis, and we're going to plot our temperature on the y-axis. And when we do, we get the following diagram. So I'll highlight our two axes. So we get these two lines, one that represents the mole fraction in the liquid and one that represents the mole fraction in the vapor. So everything we need to know about this two-phase system is set on this plot because it must follow Gibbs phase rule. So a couple things to point out. The plot is for water and ethylene glycol. Typically our x-axis will be for the more volatile component. So is it here? Since we have pure water when we have a value of 1, then indeed this is for water. Is this the more volatile component? Well, when we have pure water, we have a lower saturation temperature, which is around 70 degrees. Compared with no water, we have a composition of 0, we have all ethylene glycol, which has a higher saturation temperature of around 161. So for binary mixtures where we don't have azeotropes or some non-ideal behaviors, we should expect this downward plot trend for the more volatile species. Alright, so let's look at a composition of 50% water and 50% ethylene glycol. At a low enough temperature, we'll be below this bottom line, and we'll have one phase. This phase will be liquid. So we'll have some liquid mixture that as we increase the temperature will eventually come to this first line. Now this is our bubble point line. Since at this temperature we'll have our first bubble that will form, which will be enriched in the more volatile component, in this case water. The opposite line is called the dew point line. Since going from a vapor downwards as we decrease temperature will form our first liquid droplet. So these are also known as the saturated liquid line and the saturated vapor line. Anytime we're between these two lines, we have both vapor and liquid at equilibrium, and we call this VLE. So whenever we are within this envelope or on these lines, we could draw horizontal lines to determine the composition in each phase. These horizontal lines are known as tie lines, and we could draw them because both phases, the liquid and vapor, are at the same temperature. In this case, when we go from one phase of liquid and we hit our saturated liquid line around 87 degrees, we could draw a horizontal line to our vapor line to determine the composition of that first droplet of vapor. In this case, enriched in water with a mole fraction of 0.97. So let's say we keep increasing the temperature for our mixture. The composition of both phases will change, with the vapor becoming less enriched in our more volatile component. This means that the mole fraction of water in the vapor phase is decreasing with increasing temperature. Let's say we move up to 105 and we draw our tie line at 105. Now our vapor will have a mole fraction of 0.93, which is less. And you can see the trend of our saturated vapor line will continue to decrease our mole fraction of the more volatile component, water, as we increase in temperature. Now this part is important. Most people will think that since more of the less volatile component, in this case the ethylene glycol, is evaporating and the vapor is becoming less enriched in water, the liquid must be doing the opposite. Some will say that the liquid mole fraction of water must therefore be increasing if it's decreasing in the vapor phase. Just material balance is 101. However, that's completely wrong. Now, as we increase this temperature, the more volatile component, water, will preferentially vaporize and thus will decrease in the liquid composition as well. And we can see that on the plot. As we increase in temperature, our point on our saturated liquid line will continue to decrease. Say we increase from 105 to 135, you can see now that our mole fraction of water in the vapor phase is less than 0.7 and our mole fraction of water in the liquid phase is less than 0.1. Both decrease. Alright, so the last thing, as we keep increasing, eventually we're going to get to our saturated vapor line, at this case just above 145 degrees Celsius. Now we have all vapor at its dew point. Any further increases will get us back into one phase, which in this case is vapor. In this vapor, we'll have a composition the same as what we started with the liquid, in this case a 50-50 mixture, except now it's all vapor. So these changes in compositions with temperature can be plotted, and it's a good exercise to examine your understanding of a binary vapor-liquid equilibrium system. You can see the screencast titled Phase Equilibrium Txy Diagram for a test yourself question and explanation. The last thing to point out is that we could determine the relative amounts of each phase at a given temperature using what's known as the inverse lever rule. Let's go back to say 105 degrees Celsius. We draw an equilibrium tie line at 105 degrees Celsius connecting both our saturated liquid and saturated vapor lines. Now if we were at 50% composition, we draw a point on that line as such. So do we expect more liquid or more vapor at this temperature? We are closer to the saturated liquid line, so we would expect more liquid. And to determine the amount of liquid, we could take the ratio of the line from the mixture composition, I'll call M, to our saturated vapor line, let's just call it B, and a point on the saturated liquid line, point A. So this means that the amount of liquid compared to the amount of our mixture is just the distance MB over our total distance AB. This will give us a fraction that is now liquid. We could do the same thing if we wanted to compare L to V, the amount of liquid to the amount of vapor. In this case, it would just be the distance MB over the distance AM. So the ratio of each individual length can give you relative amounts of vapor to liquid. So in this case, we don't need to get a ruler out. We could just take the distance using our x-axis. So let's say our MB is 0.93 minus M 0.5 over 0.5 minus our point at point A, which we'll call 0.26. This gives us a value of 1.8, telling us that there is 1.8 times more liquid than there is vapor. So these diagrams are nice for determining phase states, determining the transition temperatures between phases, compositions, and the relative amounts of each phase. However, when we start doing separation calculations like those in the McCabe-Thiele method, we want to use what's known as an XY diagram. If we draw our equilibrium tie lines and record both the X and Y composition, and we do this for a number of temperatures, then now we'll generate a new plot that looks like the following. So on the left we have our TXY diagram, and on our right we have our XY diagram. On the x-axis is the mole fraction of water in the liquid, on the y-axis is the mole fraction in the vapor. And again, we get this because at any given temperature, 125, we get a point for our mole fraction in the liquid phase of just above 0.1. So that puts us right around here. Our vapor mole fraction is about 0.8. If I didn't draw my point so large, you can see it's above 0.8, which is where we're at. So drawing those equilibrium tie lines converts to this XY diagram. Note this is a constant pressure equilibrium phase diagram. This type of plot is convenient because the equilibrium compositions are plotted and can be placed on the same graph as material balance lines, which we'll see in other separation calculations. So we also want to put a y equals x line for reference. This will help us identify azeotropes, where the compositions of the vapor and liquid are the same. Check out our other screencasts on the flash and column distillation calculations so you can see how we apply these plots in practice.